The journey of transforming raw ore into precious metals is a complex one, demanding a meticulous approach to process selection. This crucial initial step lays the foundation for the entire extraction operation, dictating not only the technical feasibility but also the economic viability of a project. Optimal process selection ensures the most efficient and profitable method is employed to liberate the gold or silver from the ore. It requires a thorough understanding of the ore's unique characteristics, including its mineralogy, grade, and impurities. The selection process begins with a comprehensive analysis of the ore body. This involves determining the type of deposit, the geological setting, and the mineralogical composition. Understanding the nature of the ore is paramount in identifying the most suitable extraction techniques. For instance, free milling ores, where gold occurs in its native form, may be amenable to simpler methods like gravity separation. Conversely, refractory ores, where gold is finely disseminated within sulfide minerals, necessitate more complex and costly processes. Furthermore, the selection of the extraction process is significantly influenced by economic considerations. Factors such as capital expenditure, operating costs, and metal recovery rates play a crucial role in determining the project's profitability. The chosen method must strike a balance between maximizing metal extraction and minimizing operational expenses. This often involves a trade-off, as higher recovery rates may come at the expense of increased processing costs. Finally, environmental regulations and social acceptance are becoming increasingly important factors in process selection. Mining operations are under growing scrutiny to minimize their environmental footprint and ensure the well-being of local communities. Processes that generate hazardous waste or pose risks to water resources are facing stricter regulations and public opposition. Therefore, the chosen extraction method must not only be technically sound and economically viable, but also environmentally responsible and socially acceptable. Process development in gold and silver extraction hinges on two fundamental objectives: optimizing project economics and satisfying project requirements. These objectives, while distinct, are intricately intertwined, shaping every decision made throughout the development process. Optimizing project economics forms the bedrock of any successful mining operation. It involves maximizing the profitability of the project by striking a delicate balance between metal recovery, operating costs, and capital investment. The goal is to develop a process that extracts the maximum amount of valuable metals while minimizing the cost of extraction, processing, and refining. This requires a thorough analysis of various factors, including ore characteristics, reagent consumption, energy requirements, labor costs, and market prices of metals. On the other hand, satisfying project requirements encompasses a broader spectrum of considerations that go beyond pure economics. This includes adhering to strict environmental regulations, ensuring the safety of workers and surrounding communities, and minimizing the project's impact on local ecosystems. It also involves meeting specific technical requirements dictated by the ore characteristics, such as achieving a desired level of metal purity or handling certain impurities effectively. For instance, the presence of arsenic or mercury in the ore necessitates specialized processing techniques to prevent environmental contamination. Similarly, if the ore contains a high proportion of clay minerals, measures must be taken to mitigate their adverse effects on the extraction process. Failure to address these project-specific requirements can lead to costly delays, environmental liabilities, and damage to the company's reputation. In essence, process development is a multifaceted endeavor that requires a holistic approach, considering both economic and non-economic factors. By carefully balancing these objectives, mining companies can ensure the long-term sustainability and success of their operations. The journey to unlock the secrets of gold extraction begins in the assay laboratory, where initial testing plays a pivotal role in shaping the entire process development strategy. These preliminary tests provide valuable insights into the ore's characteristics, guiding the selection of appropriate extraction techniques and optimizing process parameters. One of the most crucial initial tests is the cyanide solubility test. Cyanide leaching has been the industry standard for gold extraction for over a century, owing to its effectiveness in dissolving gold from various ore types. Cyanide solubility tests are conducted to determine the amenability of the ore to this process. The tests involve contacting a representative sample of the ore with a cyanide solution under controlled conditions of pH, temperature, and cyanide concentration. The amount of gold dissolved in the solution is then measured to determine the gold recovery achievable through cyanide leaching. These tests are typically conducted under a range of conditions to simulate different leaching environments and optimize the process parameters. Factors such as cyanide concentration, pH, temperature, and leaching time are systematically varied to determine their impact on gold recovery. For instance, increasing the cyanide concentration generally enhances gold dissolution, but also increases reagent consumption and potential environmental risks. Similarly, elevating the temperature can accelerate the leaching kinetics, but may also increase the dissolution of unwanted impurities. The results of cyanide solubility tests provide crucial information for process design, including the optimal cyanide concentration, pH, temperature, and leaching time. Moreover, these tests help identify potential issues that may hinder gold extraction, such as the presence of cyanide-consuming minerals or preg-robbing carbonaceous matter. By understanding these challenges up front, engineers can develop strategies to mitigate their impact and enhance gold recovery. While cyanide leaching remains a cornerstone of gold extraction, achieving optimal gold recovery rates can be a complex endeavor. Several factors can contribute to low gold extractions, presenting unique challenges that require careful analysis and tailored solutions. Understanding these challenges and implementing appropriate mitigation strategies are crucial for maximizing project profitability. One common reason for low gold extractions is the presence of refractory gold. Unlike free milling gold, which readily dissolves in cyanide solutions, refractory gold is encapsulated within sulfide minerals or finely disseminated within the ore matrix, rendering it inaccessible to conventional leaching processes. Addressing refractory gold often requires pre-treatment methods to liberate the gold and enhance its exposure to cyanide. These methods include roasting, pressure oxidation, and bacterial oxidation, each with its own set of advantages, disadvantages, and economic considerations. Another challenge arises from the presence of preg-robbing constituents in the ore. These constituents, typically carbonaceous matter or certain clay minerals, have a high affinity for gold cyanide complexes, effectively stealing the dissolved gold from the leaching solution. This phenomenon, known as preg-robbing, can significantly reduce gold recovery rates. Mitigation strategies involve pre-treatment methods to passivate the preg-robbing surfaces or modify the leaching chemistry to minimize their impact. Options include using alternative lixiviants, adjusting the pH, or adding specialized reagents. Furthermore, inadequate grinding of the ore can also hinder gold extraction. If the ore particles are too coarse, the gold locked within the particles remains inaccessible to the cyanide solution, leading to incomplete leaching. Optimizing the grinding circuit to achieve a finer particle size distribution can significantly enhance gold recovery, but it also increases energy consumption and operating costs. Therefore, a balance must be struck between achieving satisfactory gold extraction and minimizing grinding costs.